Okay, so far we talked about the MapReduce, and we assume that in those examples you have cluster of computers in your server farm or data centers that can process these tasks individually. So you can use one processor or one computer as a mapping processor or as a reduction processor. Now we want to use the same strategy, MapReduce, on the OpenCL devices. So how is that going to be different? It's going to be very different from a CPU environment. If you recall that on OpenCL device, we do have a lot of processing elements. And these processing elements are organized in terms of compute unit, and then you on one processor, GPU or FPGA, you may have a number of compute units. So it's possible that you perform computations using these large number of processing elements. The major difference, however, is the memory structure. In a CPU environment, especially in this large-scale MapReduce paradigm, you assume that the processors have its own memory space, and that's it. You have full access to these memory space. But on a OpenCL device, the device memory structure is hierarchical. You have private memory, local memory, and global memory. And these three different memory structures, they have different orders of magnitude in size. Local memory expect to be kilobytes or even smaller, and for local memory expect to be in the megabytes of range or smaller, and in a global memory you expect to be in the gigabytes range. So that's roughly the order of these different memory structures in size. The processing elements, they have private memory, and the visibility, actually I should, yeah, this bullet should be in this here. So the data visibility is different from, in different scopes. Private memory is private to the processing element, so that's the finest unit of the processors. And the data in the private memory is only visible or available to the work items, but not to others. So you have, for example, you have a local variable. You can have I as a loop iteration. You can increment and then track the loops, and that's typically going to be in local memory. For the, I'm sorry, that's local memory or private memory? Okay, I meant private memory, and that's only visible to the work item itself, not visible to others. If you go up one level, you have this local memory. Local memory belongs to a compute unit, so all the work items in the compute unit can see the data in the local memory. So that's what I say. The data in local memory is visible to work items in a group, but not across groups. So let's say you have local memory for compute unit 0, and you have local memory for compute unit 1. Then the data in local memory unit 1 will not be visible or available to the any of the work items in work group 0. And finally, the global memory, it's visible to all work items. Okay, so what we are trying to do, well, at least we see there's opportunity to leverage this large number of processing elements in OpenCL device And so we want to use a MapReduce kind of approach to perform operations or address a problem like word count. So here's what we're going to have. We will need to use different work groups. If you recall that in the first lab, also in the previous several lectures, we showed you how to perform matrix multiplication. Right? We basically to partition the whole matrix into smaller pieces that we can work on, and we will assign the computation of one item to one work item, or one element in the resulting matrix to one work item. And here we would like to assign work items to perform some of the tasks that a mapping processor or a mapping computer is supposed to do. We will still have this MapReduce two big stages. Mapping stage will have all the processors to produce a key value pair or key value pairs. And the reduction stage, we expect the other group of processors to perform the reduction by collecting the results of the key value pairs and combine them in order to generate the final result. In this case, we'll need to use all the memory hierarchy. In fact, private memory, we need to use them for temporal variables, iteration variables, etc., accumulation variables. And local memory is also important in this case because we would like to perform reduction and we would like to have the result visible to other work items. So that's why we have to use local memory in order to be able to see the results, see the key value pairs from other work items. Also, we would like to use global memory, but there's a caveat that we have to pay attention here is, if you have all the key value pairs in the global memory, you end up having all the work items to compete on the memory bandwidth, in addition to the capacity of the memory. But more importantly, the bandwidth of the global memory. So it's beneficial to have some of the reduction actually done within the work group. That means we will not use the global memory. Instead, we're going to be using the local memory to perform some of the reductions. And that's why you see in this diagram, we show how we organize the work groups. So we have work group 0, work group 1, and in each work group we have work items to perform some operation. So you can think about this, what's going to happen, this part here is going to happen on work item 0, within work group 0. This is going to be happen on work item 1 within work group 0. And this similar here, this is going to be work item 0 in work group 1, and so on. So each of this work item will perform mapping operation. Mapping is basically to look at the chunk of data assigned to this work item to compute the key value pairs. So it's going to generate these key value pairs is the first part. We said earlier that we would not be able to afford to have all the key value pairs to put into the global memory and then do reduction on global memory, because that's a lot of attention on memory bandwidth. You have to push all the computation results and key value pairs out. Then you have to, again, fetch them back in order to do the computation. So it's a waste of bandwidth. So what's going to happen for this single work item, it not only performs the mapping stage, it also performs a small part of the reduction stage. And that's what we call local reduction. So the local reduction is basically to look at all the key value pairs produced by all the mapping processors. In this case, it's not actually processor, but we know it's the smaller processing elements on the OpenCL device. So the work items, each of these processing elements need to look at all these key value pairs. And because we need to access these key value pairs, so these key value pairs have to be in local memory. If they're not in global memory or local memory, that means they have to be on private memory. But if they are on private memory, then you cannot have this work item access these key value pairs. So all the key value pairs should be in the local memory, so that all the other work items within a group can access them. Because you need to do the reduction stage to combine the results. Once you have local reduction, you will generate a kind of an intermediate results. And these results are coming from each of these work items. And then these work items will be put into the global memory, where eventually one of these processing elements, one of these work items will perform this global reduction. Because global reduction is still a computation. Right? What you have available are these work items or processing elements. So eventually, for the final reduction, the global reduction, one of these work items, I don't care which one, but has to perform the final global reduction. In the work counting case, it's basically the final counting by combining all the intermediate counting results. I cover all the points here. So local memory is preferred due to speed. Each block of local memory is specific to the work item in a work group. That's what we have talked about, the memory hierarchy. MapReduce has to combine the results of multiple work groups in global memory due to data size. And the difference between this MapReduce on the OpenCL device with the MapReduce on the cluster of computers is that we have to do this local reduction and global reduction. And local reduction operates data in local memory. Global reduction receive local reduction results and produce the final result. So far, so good. Well, it turns out that we have to worry a little bit more things in order to really implement this. So there are other challenges of MapReduce on OpenCL devices. We really don't know the number of key value pairs produced by the mapping stage. In the earlier example, we showed that the results coming out of the mapping processors, they may or may not have the same number of key value pairs. Some could be having more, some less. In CPU clusters, if you run Windows or Linux, you can use malloc or new to allocate these memory spaces on demand based on the number of key value pairs you produce from the mapping process. But OpenCL kernel does not support either of them. So there's no dynamic memory allocation. You have to really specify the number of bytes that you need to use in local memory, global memory. So that's another reason that we combine the mapping stage with the local reduction stage. We have each work group transfer one results to the global reduction stage, and that will further lead to this 5-step procedure that we're going to explain next. These are the 5 steps. First, the work item in a work group forms the mapping. Instead of just producing the key value pairs, it also performs a portion of the local reduction stage. For several reasons, one of them is because the memory contention of the global memory throughput, and also use local memory, you can benefit from higher speed access. The second step is to have the kernel execute a local barrier that prevents further execution until all work items in the work group have completed their processing. We'll come back to explain more. Essentially, we need to synchronize all the work items in a work group before they perform the reduction, the local reduction. We want to make sure that all the work items perform or finish the same operation that produces the valid key value pairs. And third step is that in each work group, the work item whose local ID equals 0 reduce the work group's output to a single result. This is what we call the local reduction. This one will, this work item will be able to pre-process the key value pairs produced by all work items. The fourth step is that the kernel executes a global barrier that prevents further execution until all work groups have completed their processing. We'll show you later, but the point is that before you perform the final global reduction to compute the final result, final counting numbers, you have to make sure that all the work items have finished in all the work groups, because otherwise you maybe end up having a final result that missed some of the results from some of the work items. The final one, the work item whose global ID equals 0 will receive the result from each of the work group and reduce the result into the final result.